Okay, hello everybody. Welcome back to Markov processes. The exams I'm still working on them. They're coming along good. You'll definitely get them back this week, although it might be more towards the end of the week. There's currently no homework. I know grad students are working on something, and you are always welcome to come, ask questions in my office hour. So I don't think there's anything pending, but does anyone have anything they want to ask or discuss before we get going? It is a new day in Markov processes. We are changing over today to, for the first time, looking at a continuous time Markov process on a discrete state space. And as we do that, we're going to have a little simulation break today. Okay, so if you've been having any difficulty in this class, although it's looking pretty good as the exams are going, this is a new day, and what we're doing now does not really depend that heavily on what we've already done. So take heart. We are moving to, as I said, continuous time, but a discrete state space. And so what we're going to have is something like a queuing model, where on the y-axis we have a number of customers in the system. And maybe we start with 0 customers, and time goes along, and at some random time point, we get a customer. So this will look like kind of like a step function. And at some random time, we'll get another customer. And you can see the way I've drawn these that, this time interval and this time interval are different. These are going to be continuous random variables with a distribution. But for now, we're still talking about discrete state spaces. So as we move in here, I want to remind you a few things about continuous distributions and PDFs and things like that. And for the record, still discrete on the state space. So we have the idea of a PDF, a probability density function, and a CDF, a cumulative distribution function. And so we have a random variable X is a random variable with a probability density function, affectionately referred to as a PDF. And this is going to be some function f of x, and this is no longer probability. So far we've had discrete random variables where we've talked about the probability that x equals x. And for a continuous random variable, there's just so many options that the probability that x is going to equal one particular number is going to be 0. So for example, if I want to measure the height of the next person to walk into this room, and assume that I have infinite accuracy in my measuring, then what is the probability that person is going to be 67.2138824 inches? It's very small, very, very small. And if I add more decimals, it's actually vanishing. So the probability of seeing someone at exactly a certain height is 0. And so for this reason, we had in the discrete case a probability mass function. I actually call them all probability density functions. Some people switch to density when they're talking about continuous random variables. I call them all densities, except that with the caveat that it means something different, whether, if I have a discrete or continuous random variable. But we haven't named our probability mass functions from before. They're usually called f of x. Now that's the discrete case, and that is not what I'm going to do here because this probability is always 0 for a continuous random variable. And I need to emphasize that. So I am going to sort of caret in a continuous random variable with some probability density function. So I'm sure you all know, so I'm probably boring most of you, that the PDF is a curve under which area represents probability. And so if you want to find the probability that x is in certain regions, then you're going to have to do some integration. And I'm going to draw a PDF. So this is x, and this is my f of x. And if I just put down two numbers like a and b, and a is less than b, and I want the probability I'm in this region, then I'm going to have to integrate the PDF. So a to b, f of x dx. And because the area of those lines is 0, we don't have any area in those lines. This is going to be the same thing if I have strict inequalities or strict on one side and not on the other. There's no area on those lines, so it'll be the same thing. So hopefully that's not new. And then the idea of an expected value. The expected value of x, this is a probability weighted average. And in the discrete case, let me stick this over here. The expected value of x is the sum over all x of x times the probability that x equals x. So if we're calling that probability f of x for a probability mass function, then you can really see the analog over here. I'm going to go back to the left. I'm going to integrate over the whole world in this one-dimensional case, x times the PDF for x. And you've probably seen this kind of integral as a center of mass in calculus. It's like a balancing point for this distribution. And it never hurts for us to talk about the integral from -infinity to infinity. So random variables have a support, and the support, well, the PDFs have a support, and the support of the PDF is the place where the PDF is non-zero. It's a little different than the domain. So PDFs are usually defined everywhere, but they may be 0 in a whole lot of places. And it wouldn't hurt for us to write integrals in general from -infinity to infinity, because this PDF may be 0 in a lot of places. So if we always write -infinity to infinity, the PDF will take care of sort of cutting the limits of integration down. So there are two continuous distributions that are going to be huge in Markov processes. One is the exponential distribution. So here's a definition. A random variable x has an exponential distribution. Now there's a parameter to describe this, and people use two different kinds of parameterizations. So an exponential distribution with rate lambda, so this is a parameter that we're going to have to give to this, greater than 0, if x has PDF f of x equals lambda e to the minus lambda x, and that is for all x greater than or equal to 0, and it is 0 otherwise. And this equality doesn't even have to be there. If you've taken other courses with me, you'll know I'm big on these indicator functions for describing PDFs. I don't think I don't think we need them as much in here, so I'm not bringing them up. But if you're happy, if you're used to or happy to use indicators, by all means do it. So rate. We're going to see where this exponential distribution comes from. Usually when you're introduced to this distribution, it is not through like an experiment. Like we can define the binomial distribution by imagining a sequence of trials with success and failure and having n of them and fixing the probability of success from trial to trial. And, and then we define a binomial distribution. This one at first doesn't seem like it's coming from anywhere other than it's a PDF that integrates to 1. You need two things for a PDF to be a PDF. You need it to be greater than or equal to 0, and you need for it to integrate to 1. And right now it just looks like I made up a function. But in this class, this is actually where you really get to see the importance of the exponential distribution. And it's going to come out of some very minimal assumptions about a process that's coming up. I'm going to make really super minimal assumptions, and we're going to see that the exponential distribution kind of springs out of the formulation of our Markov process. So it will be a little more constructive rather than, but right now it's just a PDF. Let's talk about the expected value or mean for x. So the function is 0 for x less than 0, and then it's It's this exponential. And right now I'm going to integrate over the whole, well, if you were to integrate the entire PDF from minus infinity to infinity, then this would correspond to minus infinity to 0. And over that region, you're integrating 0. And then 0 to infinity, you're integrating the interesting part. So going back up to the expected value, I have x times the PDF dx. And then as I was saying over here, this PDF is 0 for some of this region of integration. So this is going to be equivalent to integrating from 0 to infinity x times lambda e to the minus lambda x dx. And if you do this, and it's an integration by parts, you'll get 1 over lambda. So I have written my exponential PDF with lambda. I called it a rate parameter. And for us, this is going to be an inter-arrival time. For like a queuing system, we're going to say the time between customer arrivals is exponential with a rate of 2 customers per hour. So in this class, we're going to be really centered on rates. But as you've seen here, the mean of this distribution is 1 over lambda. And if you want to parameterize the distribution in terms of the mean, then you need to use 1 over lambdas up here every place that I used a lambda, and then your mean will come out to be lambda. So people parameterize the exponential 2 different ways, and then to describe this, we write x, squiggly line has the distribution exp for exponential, and then most books just use a lambda. And the problem with that notation is you're not sure which PDF they're using. Is it the one I wrote down, or is it the one that has 1 over lambdas in place of lambda? So I like to be really specific and say x has the distribution exponential with rate lambda whenever I mean this PDF. And then we'll rarely use it actually, but if I write exponential with mean lambda, that's going to mean that the PDF is 1 over lambda e to the minus 1 over lambda x for x greater than or equal to 0. So again, most places are going to, books and internet sites, they're going to write that, and then you're going to have to figure out what the context is. But I'm never going to write that. So I'm going to be really specific. So another function of interest, which we're going to need today for our first simulation algorithm, is the idea of a CDF, a cumulative distribution function. In probability and statistics, we almost always denote these. Let me get a new board. We almost always denote these with a capital F. And so X has a CDF F. And what that means is that this capital F of X is defined to be the probability that capital X is less than or equal to some argument little x. And this is true for discrete or continuous random variables, but in the continuous setting, you're going to compute that probability by taking the PDF and integrating up to some x. So this is going to be the integral from minus infinity up to x of the PDF, the lowercase f. I usually like to give it a different letter if I'm plugging in an x. For the exponential distribution, this is a CDF you're going to come to know and love. I know you know a lot of PDFs off the top of your head, but most people don't walk around with a lot of CDFs in their head. But for the exponential distribution, I'm going to take x exponential with rate lambda, and the CDF, the cumulative probability function. So we're integrating under the curve and accumulating all the probability or area up to x, is going to be denoted by a capital F. It's going to be the integral minus infinity up to x of the correct PDF. In this case, the PDF is 0 for negative values of u. So we're going to end up going from 0 to x, lambda e to the minus lambda u du. Or you can use x's in there. Again, I think it's weird to plug in x for x, but whatever. And if you do this integral, it's just an e, right? There's no like parts or anything like that. You're going to get you're going to get 1 minus e to the minus lambda x. And this is something we're going to use so often that you don't have to memorize it, but you eventually we'll definitely know it without thinking about it. So it's time for a simulation break. We talked about simulation for discrete random variables, and we talked about it by chopping up the unit interval, grabbing a uniform and seeing where it falls in order to assign certain values. And so what are we doing here? So let me see, simulation of a continuous random variable. And this is one-dimensional. We're working our way up. So this simulation algorithm only works if you can write down the CDF in closed form. And believe it or not, we can't even do that for the ubiquitous normal distribution. We need to be able to write down the CDF, and we need to be able to invert it. And if you can't do that, then you move on to the next algorithm. And if you can't do that, you move on to the next algorithm. And that one will have you bounding the PDF by something that you can integrate. And if you can't do that, you move on to the next algorithm. And this is what keeps me in business from day to day. I come up with algorithms for people who have run out of options. So this is gonna, here we're gonna assume the CDF, I won't say exists, but we can write it down, is tractable and invertible, or we can get a closed form expression. So here are the steps. Suppose that X has cumulative distribution function, capital F, and suppose that U has a uniform 0, 1 distribution. So that's the random number we're assuming our software can give us. So what I want to do is grab a uniform from the random number generator and output the CDF inverted with U plugged in. And that is going to be one value from your distribution. Now, if that doesn't make sense, we're going to actually see this in action. But this is called, let's prove this and then let's check it out. So this is called the inverse CDF method. I don't know who came up with that. Yeah, before we do an example, let's prove that. So my claim here is that the CDF itself is not random, but we're plugging in a random variable. And now that's a random quantity. And my claim is that this has the same distribution as the original X. So if we're outputting numbers in this way, we're outputting X's, essentially, something that behaves like an X. And to prove this, I just want to remind you about the CDF of the uniform. I think we'll probably, yeah. So if U is uniform 0, 1, then that means we have a flat line probability density function between 0 and 1, and the total height has to be 1 because the total area has to be 1 under the curve. And so if you take a value of X in between 0 and 1 and integrate up to X, you get the area of a rectangle, which is X. So the probability that U is less than or equal to, probably should have used a U to make that look nice, but is just X, as long as X is between 0 and 1. So let me be a little more careful here. And I'm going to use a U. I'm going to use U as an argument. So this is going to be 0 or U. I replace the X, or 1. And it's going to be U if U is between 0 and 1. And it's going to be 1 if U is greater than or equal to 1. So that's like saying, what is the probability my uniform is less than or equal to 7.8? It's always between 0 and 1. So that's going to be less than or equal to 7.8 with probability 1. And it's going to be 0 when U is less than 0. So this is 1, but what is the probability the uniform is less than or equal to negative 1.14? That's not happening. And so here is a piecewise defined CDF. So we tend to always use this capital F for CDFs, but if you're talking about multiple CDFs, then you might add a subscript like a U and then an argument to distinguish between a CDF for X, which is what I'm trying to simulate here, and the CDF for U. So I want to go back to my claim to say that F inverse of U, again, F inverse is not random, but when you put that random variable in, you have randomness there, and it's going to be different as U changes. And I want to show that it has the same distribution as X. So yeah, let's look at the distribution of like a new random variable Y that I'm going to define to be F inverse of capital U. So if I look at the CDF for Y, this is the probability that Y is less than or equal to this little y. And the capital Y is defined, so I'm going to plug it in as capital F inverse U. So yeah, done with that phrase. And now I'm going to apply the CDF to both sides. A CDF, because it accumulates probability, never decreases. It could actually be flat. If you have a PDF that is like 0 and then comes up again, and you are trying to accumulate area up to a point X. If your X is in here, then the CDF is going to be all of the area down here. And it's going to stay that way for all of the X's in here. And so for a PDF like this, your CDF, which has cumulative probability, is going to be increasing, and then at some point flat, and then eventually increasing again. But it is a probability, so it's always between 0 and 1. And it's going to approach 1 as you go off to infinity, because, for example, for Y, the probability that Y is less than or equal to infinity is 1. And it should always approach 0 when you go off to negative infinity, because the probability that Y is less than or equal to negative infinity is going to be 0. But my point is that CDFs are non-decreasing, and CDFs that are assumed to be invertible can't flatten out, or they wouldn't be invertible, so they are strictly increasing. So this F I'm applying to both sides is increasing, and that means it's not going to affect the inequality. So when I apply it to the left side, I get F of F inverse of U, and when I apply it to the right side, I get capital F of Y, which is not a random quantity, but a number. And because the CDF is always between 0 and 1, then I'm in this case for the uniform. The probability that U is less than or equal to something is the thing. And in this case, that thing is F of Y. So this equality here was because U is uniform 0, 1. We're using the fact that the probability U is less than or equal to little u is little u if U is between 0 and 1. And what I have here, this was the original given CDF. Suppose X has CDF F. So this is representing the probability that X is less than or equal to the argument Y. I.e., I guess I could have stopped here. The CDF for X. We found the CDF for Y. Y was defined in this funky way. It's the same as the CDF for X. So this random variable right here has the same distribution as X. And if you're used to defining distributions in terms of PDFs, probability density functions, then you take what we just did and take the derivative of both sides, and you'll have that the PDF for Y is the same as the PDF for X. So as an example of this inverse CDF method, I want to simulate values from the exponential rate lambda distribution. And lambda has to be given for you to do this. So the exponential has a nice CDF that can be written in closed form and inverted. The CDF is 1 minus e to the minus lambda x. And so if you set this equal to y and invert the function, you'll see that the inverse CDF I'm going to write it as a function of x, is -1 over lambda times the log of 1 minus x. So what I'm about to do in that R code is to produce uniforms and plug them into this function and output them. That's it. It's 2 lines. Grab a uniform, put it into the function. And if we want to see it and make a histogram, then it's 3 lines. And by the way, if you take a uniform, that number is equally likely to be between 0 and 1. So it's just as likely to be here as it is here. And no matter what point you kind of pick on here, you can reflect them over the line x equals 1/2. And so if 1 minus x is, if we're plugging in a uniform, my point is that 1 minus a uniform is also uniform 0, 1. So I could code this with this guy over here just being x, because it would still be just another uniform 0, 1. But I didn't. So now let me go to simulation. I wrote a little script using the inverse CDF method, and let's talk about the results. Script 1. Okay, what you're looking at here is, you guys are all in the way. I simulated one single exponential, and I used the rate of, who knows what I used. What did I use? I used lambda equals 2. And so what are you expecting to see? Nothing with one draw from this distribution, but I'm making a histogram, and you'll notice I have something called density on the y-axis. So when people make histograms, they put one of 3 things on the y-axis. One of them is the count. So if I were to simulate 1,000 values, then the height of this bar would be the number of values that fall into this little bin down here. By the way, I did bin this up in increments of 0.1. So what this looks like is, now it looks like this bar starts at 0.1 and ends at 0.2. So this is saying the one value that I simulated is between 0.1 and 0.2. But as I was saying, some people use counts or frequency on the y-axis. Some people use proportions or relative frequencies. And in that case, they would make a bar with height 1, because 100% of this data is in that interval. Again, I've only simulated one value. But what we're using is density. And density is the number such that the area of the bar is the proportion of values in your sample that fell into that bin. So I had one output. It fell between 0.1 and 0.2. And I made a histogram of one thing, and it's at a height of 10, because 10 times that base of 0.1 is 1. So the total area of this histogram is always 1. And the reason we want to do that with density is so that we can match it to a PDF. So it's on the right scale for the PDF for the exponential. So I'm going to simulate another value. Woohoo! So now I have another value somewhere else. It looks like it's, I don't know, 0.7 to 0.8. And each of those bars has area 0.5 now. You multiply the base of 0.1 times the height of 5. I'm going to do another one. Okay, how interesting. Another one. Oh, can I get 2 in one bin? Hasn't happened yet. So now what I'm going to do is just run it up to time 20. I put pauses in. This is not the slowness of R. I wanted you to see this, but you can see that some of the bins are getting more values in them. Come on. Okay, so here's a histogram of 20 values using that inverse CDF method. So I grabbed 20 uniforms and I put them through the inverse CDF for the exponential. What are we trying to see? Because I have density on the y-axis, this is supposed to match the PDF. My lambda was 2, so I'm going to superimpose the PDF, 2 times e to the minus 2x on top. That is not looking so good, but that's because I only have 20 values. So we're simulating precisely and without error from the exponential distribution, assuming you have a perfect random number generator, because there's always someone in the back that goes, I think you mean pseudo random. Yeah, assuming that I have perfect uniform 0, 1s, then what we're doing has no error and there's no convergence. We're grabbing values from the exponential distribution. So now I'm about to kick it up to 100 values. It's looking better. And now I'm just going to skip the iterations and go all the way to, and this is live, anything can happen. Go all the way to 100,000 values. And there you can see the curve. It looks really, really nice. And you can't see the niceness until you get a lot of values. So that's the results of the inverse CDF method. And that's one way to look at it if you know the underlying PDF to figure out whether or not you're doing a good job. But you can never really tell that you're doing a good job when only simulating a small handful of values. Yes, thank you for bringing it up because I wanted to mention that. You have probably no need to simulate an exponential because most software, including R and Python and MATLAB, can do that under the hood, right? So you can just ask it for an exponential. But what we're doing here is trying to figure out what's going on under the hood so that when you need to simulate from your own distribution for some research you're doing later, that's not a nice known name distribution, then you have methods. R or Python or whatever you're using is not going to have a black box for every distribution. So our goal here is, to go under the hood. You couldn't do it for the normal because we can't write down the inverse CDF. Now, I suppose you could do something numerically, but there are much better methods for the normal distribution, which we'll get to. And what we did before with our discrete random variables, we were doing that interval chopping. So we had X like discrete, and just as an example, suppose it takes on the values 0, 1, and 2 with some probabilities. I'm going to keep this nice and simple, 1/2, 1/4, 1/4. So we took a uniform 0, 1, and we chopped up the interval into an interval of length 1/2. So that means I'll go from 0 to 1/2, and an interval from 1/2 to 3/4. So that's a length of 1/4, and this final length of 1/4. And we would grab a uniform. Well, we actually haven't done this simulation. We only talked about it, but you would grab a uniform and it will fall in here with probability 1/2. It'll fall in here with probability 1/4 and in here with probability 1/4. So if your uniform falls in the first bin here, you should set your output equal to 0. And if it falls in this next one, you should set your output equal to 1. And if it falls in here, you should set your output equal to 2. That's what we've talked about so far. But this is actually an inverse CDF method. It's just a generalized inverse. So this is the inverse CDF method with a generalized inverse. I'll tell you exactly what I mean by that. The CDF for a discrete random variable is a step function. So here I'm going to take X and I'm going to plot the CDF capital F. And the probability that this random variable X is less than or equal to negative 4.4, that's not happening, that's 0. So the CDF is 0 out here. And then once we get up to 0, so X less than or equal to 0, this is the probability that X equals 0 in this discrete case, and that is 1/2. So the CDF evaluated at 0 is up here at 1/2. So like a step function. And then you go along until you hit 1, not accumulating anything. And then at 1, you accumulate 1/4 of the probability to bring you up to a total of 3/4. And then you go along and stay flat, not accumulating anything until you hit 2. And then you jump up to the final height. You add another 1/4 and you are up at 1. So this is not invertible because you need to be able to take something off the y-axis and figure out where it came from on the x-axis. But if we use the idea of a generalized inverse, and you do not have to know this for this course, it's just for fun, the generalized inverse, F inverse Y, can be defined to be the infimum. So if you're not up on infimums, just replace that with min. An infimum is essentially a minimum, but a little fancier. And for those of you that know about infimums, I'm sorry, I just treated it like that. But it's going to be the infimum over all x such that f of x is greater than y. That is how you define a generalized inverse for a function that's not invertible. And look what happens here. So if I grab a uniform, then that's like in between 0 and 1. That's like grabbing something in here. And if I invert that, so I put it through the inverse CDF, so maybe y is somewhere in here, then I want to find the x that is the smallest x for which the CDF jumps over y. So in here, the CDF is below y, but right here is where the CDF jumps over the y line. And so F inverse of this number, I don't know, I didn't give it a number, is going to be 1. And so you see the interval chopping happening on the y-axis, because anytime the uniform falls between 0 and 1/2, it's going to output a 0. And anytime the uniform falls between 1/2 and 3/4, it's going to output a 1. And anytime the uniform falls up there, we're going to get a 2. And that's exactly what we did with our very basic interval chopping method. Yay! So what do you do if you can't write down the CDF in closed form and you can't integrate it? We'll be getting to that. And probably by today, we're going to be talking about our next simulation algorithm, which is called the accept-reject algorithm due to John von Neumann. But first, a little break from our simulation break. So let's go back to Markov. Not really, it's not very Markov, but I introduced an important continuous distribution, the exponential distribution. And there's 2 distributions in Markov in the continuous distributions that are important, the exponential and the gamma. But before I review the gamma, I wanted to talk more about properties of the exponential distribution, namely the so-called lack of memory or memoryless property of the exponential. This is going to be really key to a Markov process. I'll explain that after I describe the lack of memory property. So suppose that x has the exponential distribution with some rate equaling lambda. Then we know the CDF is the probability that x is less than or equal to x. And for this exponential, that's 1 minus e to the minus lambda x. And so this gives us the so-called tail probability, the probability that x is greater than x. That's going to be 1 minus the CDF. And when you subtract this from 1, you end up with just the e to the minus lambda x. Doesn't look like an x up there. This function is often denoted as a capital F with a line over it for this kind of the opposite of the CDF. And that has nothing to do with lack of memory. So this is really where I should have put the title. Suppose that x has this exponential distribution. I'm going to let little x and little y be some numbers greater than 0. And we're going to consider the probability that x is greater than x plus y, given that x is greater than x. We know how to do this. We're really old pros at conditional probability. This is the probability that x is greater than x plus y and comma intersection, and x is greater than x over the probability that x is greater than x. Because x and y are positive, or because y is positive, if we're greater than x plus y, we're already greater than x. So the intersection of those 2 events is the probability that x is greater than x plus y. And in the denominator, we still have what we have. And so we have these two tail probabilities, which can't read that. I can write this in the numerator as e to the minus lambda times x plus y. And in the denominator, e to the minus lambda x. And so we'll get some cancellation and we'll get e to the minus lambda y. And that is the tail probability evaluated at y. So this is the probability that x is greater than y. And so from this left side to this right side, this is called the lack of memory property of the exponential. And it could be best understood if you're talking about x as the lifetime of a component of something or an arrival time. So for us, it's going to be arrival times, inter-arrival times for customers in queues. And this is saying, given that you've waited more than X units of time, what is the probability that you're going to have to wait at least Y more units? It's just the probability you have to wait at least Y units. The exponential distribution kind of forgot about the initial wait. And although I haven't defined a Markov process in continuous time, this is going to be so key for the Markov property. Because if we are measuring customers, like a number of customers, and they are coming in at random time points and jumping up and whatever, if we come in at an arbitrary point in time, like here, I'm going to call it t, make it look continuous. Even though I haven't defined it, the Markov property, where you go next, should only depend on where you are. It shouldn't depend on where you were, and it also shouldn't depend on how long you were where you are. I have to define it, but we should be able to know where we're going to go without knowing how long we've been in that state. And for the exponential distribution, if we say that the times here, and they're not meant to look evenly spaced, but if this is an exponential amount of time and this and whatever that goes to is an exponential amount of time, and you walk in and interrupt the process at time t, the amount of time until the next arrival is still exponential with the same rate. And that's very Markov. We don't care how long we were there. And we're going to prove that once we have the definition of a continuous time Markov on a discrete state space, we're going to prove that the exponential, the times where the chain changes values has to be an exponential. And you know where that comes from? That comes from the reverse of this lack of memory property. So the next thing I want to claim is that the exponential distribution is the only continuous distribution with this property. Except potentially if you make something up, like you flip the exponential over the x-axis to make negative values or something. But yeah, so this is a cool thing that gets an asterisk in a circle. The exponential distribution is the only, I don't know if I said it when I just said it, it's the only continuous distribution with this lack of memory property. And we'll prove it in a second. But again, you can see why this is going to be important for a Markov process, even though I have yet to define it. By the way, we're only going to prove this right now for this continuous distribution model. But if you're talking about discrete random variables, there is a random variable there that has a lack of memory property, and only one, and that is the geometric distribution. So let's prove this. So I don't have an exponential distribution in sight. What I have is, I'm going to suppose that x is continuous on 0 to infinity with this property. Okay, I said nothing about the exponential, but what does this mean? This means suppose that we have a little x and a little y greater than 0, then we are assuming that we have the property, the probability that x is greater than x plus y, given x is greater than x. This is the probability that x is greater than y. That's our assumption, and we want to get the exponential distribution out of this. So if you write the left-hand side as the intersection probability, just write out the definition of this conditional and do the same thing we did before. If x is greater than x plus y, then it's definitely greater than x because my x and y are positive. So there's redundancy there. And this left-hand side can be written as x greater than x plus y over the probability x is greater than x. And I'm just going to bring down the right-hand side. So starting out with the supposition that we have the lack of memory property, that means we have this. And that implies that we have the probability that x is greater than x plus y is the product of the probability that x is greater than x times the probability that x is greater than y. I'm writing bigger and bigger as I get more excited about this. So in terms of tail CDFs, this is the CDF. So up here, I'm going to let f be the CDF or cumulative distribution function for the random variable x that has this lack of memory property. So I get that tail CDF with a line over it evaluated at x plus y is equal to the tail CDF. It's not a tail CDF, it's a tail probability. The tail probability that x is greater than x times the tail probability that x is greater than y. So that's just saying the same thing as the line above in our new notation with this f bar. So I am going to factor on the, you know what, I'm going to subtract an f bar of x from both sides. So I'm going to subtract it over here as well. And I'm going to go ahead already and factor that out. So I'm left with f bar of y minus 1. So I subtracted f bar x from both sides, and then I collected some things on the right side. So this one, yeah, why do I always get to that? This one over here, I can actually write this as f bar of 0. I'm trying to see a derivative here because f bar of 0 is the probability that x is greater than 0. And for this distribution, that's definitely true. So this probability is 1. So I could replace the 1 over here with this f bar, and we're sort of seeing a derivative once I divide by something. So let's do that. I am going to divide both sides by y. So I get f bar x plus y minus f bar of x over y is equal to this f bar of x and then f bar y minus f bar 0 over y. And so we're going to let y go to 0. And on the left, we have the derivative. We have f bar prime. I need the prime out there at x. And on the right, this is just sitting there as y goes to 0. So I have f bar of x. And then over here, I've got f bar prime 0. So let me know if there's anything I can clear up. But we started with the lack of memory property, and I'm about to solve for f bar. And we're going to see that that matches the exponential distribution's f bar. So I think this notation is getting really kind of cumbersome. This f bar prime of 0 is a constant. And then this f bar x is some function. And obviously on the left, I've got the derivative. So I don't know if this is useful or not, but if you have like a differential equation like this, then you may recall that you can move the g of x to the other side. And then you can integrate both sides with respect to x. And on the left side, you get the log of g of x, because if you take the derivative of that log, you get the derivative of g over g, plus a constant. But I'm going to keep all my constants together on the other side. So on the other side, when you integrate c with respect to x, you get c times x plus a constant that I will call d for some constant d. And trying to solve this differential equation for the g, I'm going to take e to both sides. This is e to the cx plus d. So for us, our g is f of x bar. And I do know an initial condition. Remember, f bar of 0 is the probability that x is greater than 0, and that is 1. And so if you have the initial condition that g of 0 is 1, then you have one of those constants. If you plug in 0, you get e to the, you get just e to the d. And if that's 1, then that implies that your g of x is your e to the cx. Going back up to what I actually care about, instead of g of x, we're looking at f bar of x. And this has to equal e to the cx for some constant c. But this is a probability, and it needs to be between 0 and 1. So c must be negative. But instead, I will write f bar x equals e to the minus cx for c positive. And there you see the tail of the exponential CDF. So this implies that the CDF for x is f of x equals 1 minus e to the minus cx. And the PDF is little f of x is the derivative, which is c e to the minus cx. And there is the exponential PDF. So maybe I made that longer than it had to be, but we started with the assumption that we had this lack of memory property, and we got to an exponential CDF. Let's talk about our second important continuous distribution, the gamma distribution. So the continuous random variable x is said to have a gamma distribution with parameters a and b, which both need to be, I don't want to use a and b. Let's use alpha and beta. I think, yeah, let's use alpha and beta. Usually like to stick to Greek letters for parameters. If x has the following PDF or something close to it. But just like with the exponential PDF, there is an option to flip a parameter here. But I'm going to write it this way, so it kind of matches with our exponential. The PDF is going to be 1 over capital gamma of alpha. Now that is something called the gamma function, which we're going to review. And then beta to the alpha, or introduce, and then x to the alpha minus 1, and then e to the minus beta x. And that is for x greater than or equal to 0, and it's 0 otherwise. Just like some people write the exponential with the lambda, where we had the lambda, and some people write with 1 over lambda. Some people write this distribution with the beta replaced with 1 over beta. So we will write, when we mean this distribution, x squiggly line has the distribution gamma alpha beta. This is another capital gamma, and it means something different than the capital gamma in the PDF. So if it has only one argument, it is the gamma function, which we need to define. And if it has 2 arguments, it's the name of a distribution. Some people, when they write this x squiggly line, gamma alpha beta, they actually mean this PDF with all of the betas replaced with 1 over beta. So you do need to be careful if you're reading a book or paper or, a website. This alpha parameter is known as a shape parameter for reasons that we're going to see in a few minutes. And the way I have this parameterized, this beta is known as an inverse scale parameter. And the people that put 1 over betas in place of my beta, their beta is known as a scale parameter, which sounds simpler, but for the study of Markov processes, this is going to be a much more useful form of the PDF. So right now, it's just a definition of a PDF. We're going to see the role of that shape parameter. But before I can go any further, I need to define this gamma function. So let's do it. Okay, so the gamma function this is defined for a parameter alpha. Did I say that? Yeah, the alpha and beta here have to be greater than 0. So this is defined for alpha greater than 0. The gamma of alpha, again, 2 parameters in there, it's the name of a distribution. 1 parameter in there, it's this gamma function. So this is defined. You don't know what this colon in front of the equal sign means is defined as the integral from 0 to infinity, x to the alpha minus 1, e to the minus x dx. That's the definition of the gamma function. And check this out. If you integrate from 0 to infinity, I'm going to look at most of the PDF that I gave you above. I'm going to ignore the gamma function. The rest of it was beta to the alpha, x to the alpha minus 1. Let me put a note in front of this because, like, where am I going with that? That just came out of nowhere. Note that. So then e to the minus beta x dx, I could sort of move things around and collect like a beta x to the alpha minus 1 and e to the minus beta x, and then I have a remaining beta dx. And if you let u be beta times x and do a u substitution, you get the integral of u to the alpha minus 1 e to the minus u du. This whole thing becomes du. And because beta is positive, the new limits of integration still go from 0 to infinity. So note, u is going to go from 0 to infinity. And that is the gamma function. So this is the PDF without the gamma part. And so you can make up your own PDF now. I'm going to scroll back up to the original PDF here. All you have to do is come up with your favorite function that is non-negative and integrable, where you can do the integral and it's something finite. And then you define that finite to be a constant named after yourself. And then you put 1 over the constant in front, and you've made up your own distribution. Okay. So that's the definition. We don't care that much about the definition. What I really care about are, oh, let me just recap that it's not defined with a beta in it, but when you put the beta in, it will disappear if you do a change of variables. And so it is the constant that makes our original PDF equal to 1. So let's talk about some properties. The gamma function has a lot of really neat properties, 3 of which we care about in here. The first one is that gamma of 1 is 1. And to prove this, you just write out what gamma of 1 is. It is the integral 0 to infinity of x to the 1 minus 1 e to the minus x dx. That's the integral 0 to infinity of e to the minus x dx. And that is 1, either because you integrated it or you realize that that's a PDF. That's the exponential PDF with rate 1. So it must integrate to 1. So that's the first property. The next out of 3 properties is for an alpha, which has to be greater than 0. But in this property, for an alpha greater than 1, the gamma of alpha can be written as alpha minus 1 gamma of alpha minus 1. And to show that, let's do it. So proof. Gamma of alpha, by definition, is the integral from 0 to infinity of x to the alpha minus 1 e to the minus x dx. And I'm going to do integration by parts. All right, so that's the integral of u dv is uv minus the integral of v du. And here I'm going to let u be x to the alpha minus 1, and du is then alpha minus 1, x to the alpha minus 2 dx. And I'm going to let v be e to the minus x, and dv is negative e to the negative x. And when we break this into parts, hopefully we will pop out the gamma function with one less alpha. So continuing from here, this is u times v. So I get x to the alpha minus 1 e to the minus x. And this is a definite integral. So I do want to be evaluating this stuff from 0 to infinity minus, and because of this negative out here, I'm just going to make this a plus right now, the integral from 0 to infinity of the other stuff. So I'm going to pull out the alpha plus 1, minus 1, alpha minus 1, integral 0 to infinity, x to the alpha minus 2, e to the minus x dx. So there you see the gamma function, but the alpha has been decreased by 1. So this is gamma of alpha minus 1. And then over here to deal with this, you would be plugging in, when you plug in 0, you get 0 times, let's assume that alpha is greater than 1. When you plug in 0, you get 0 times 1, which is 0. To quote unquote plug in infinity, you really want to take a limit. If alpha is greater than 1, the x is blowing up, but the e is coming down, and it's coming down faster, and it's taking over. And you can show that with L'Hopital's rule, but this is going to be 0 when you evaluate it. So I started with gamma of alpha, and we ended up with alpha minus 1 times gamma alpha minus 1. Okay, third and final property, not that there aren't more. For an integer, now that alpha is a real number greater than 0, and for that previous property greater than 1. For an integer n greater than 1, if we look at gamma of n, I'm not going to write what this is yet up here. Let's just go to the proof. What am I proving? Gamma of n by property 2 can be written as n minus 1, gamma of n minus 1. And if you apply property 2 again, you can keep that n minus 1 there and rewrite gamma of n minus 1 as n minus 2, gamma of n minus 2. And you'll eventually get all the way down to 1. So n minus 1, n minus 2, down to 1 times gamma of 1, and gamma of 1 is 1. So we get n minus 1 factorial. So that's the property that I never stated. I wanted to talk about the role of alpha. I'm going to do this really fast. What I really want to get to is I have another simulation queued up for you, and I only have 2 minutes. So I said that alpha is a shape. You know what? I'm not going to get to it, so I'll stop rushing. It's a shape parameter. And alpha has to be greater than 0. And if you look at the form of the function, x to the alpha minus 1, e to the minus beta x, and then the other stuff sitting out front is just constants, then you can see that in the case that alpha is greater than 1, you've got x to a positive power. And so when you plug in x equals 0, it starts at 0 and it increases until the e to the negative power takes over and drives it back down. So you get something, like this when alpha is greater than 1. And when alpha equals 1, and you can move that lump around, but when alpha equals 1, you get x to the 0. So the only x part here is e to the minus beta x, which is looking like an exponential distribution. And in fact, if you put the whole PDF together, 1 over gamma of 1, beta to the 1, x to the 1 minus 1, e to the minus beta x, this is 1, this is 1, and you get beta e to the minus beta x. So you get an exponential distribution starting at beta and going down exponentially. And finally, if alpha is less than 1, it does have to be greater than 0, then the x to the alpha minus 1 gives you like an asymptote. So it is, going off to infinity in this direction. So next time, we're going to talk about the fact that if you sum up exponentials, you get a gamma distribution. And the reason that's interesting to us is if you make people have exponential inter-arrival times in your queuing system or some kind of event system, then the time until the nth arrival will have a gamma distribution. And that information is going to be important to us. We're also going to continue simulation and talk about the accept reject algorithm before going on to define Markov chains on a continuous time but discrete state space. Next time on Markov processes.